Okay, now in order to do this, the overall general logic is that we're going to form this physical triangle, and then we're going to aggregate the physical links into one logical port. Okay, behind the scenes, somehow the switches are going to have to be synchronizing the control plane so that they both agree that the MAC address for the end node is located out this logical multi-chassis lag as opposed to the normal point-to-point link. So we saw in our previous example when we were looking at the show MAC address table and looking at the show spanning tree, from the point-to-point lag, where a spanning tree is actively forwarding over the logical interface, and then the MAC address table is learning the MAC addresses over the logical link as well. But from a multi-chassis lag point of view, we need to make sure that this output would be equal, or this control plane information would be equal between the member switches of the multi-chassis lag, because otherwise we might have some traffic forwarding problems, or basically black hole traffic as it's going down to the final access node. Okay, so how specifically we're synchronizing the control plane is going to be some sort of proprietary implementation based on the specific flavor of the MLAG. Okay, but from the downstream device, the end result is that the access device, like the end server, is going to see the access switches as if they were one logical box. Now, the problem with this, though, is that we're breaking the normal loop prevention mechanisms of spanning tree. So we need some sort of additional mechanism behind the scenes that's going to implement new loop prevention. Okay, and final result is that we're going to be able to do active-active forwarding. Now, how specifically this is implemented, though, like I mentioned, is going to be proprietary. So if you're looking at Juniper's implementation versus Cisco Stackwise, VSS, VPC, they're not going to be compatible with each other. But the specific implementations within our particular scope would be Catalyst VSS, which would be on like your 6509s. Cross-stack Ether channel would be on your like 3750 stack, 3850 stack. Then within our particular scope, it's going to be virtual port channel on Nexus. But really, at the end of the day, all three of these things mean the same thing. It's that there's multiple chassis, so multiple physical switches that we're virtualizing into one logical chassis, and we're synchronizing the control plane between the two of them. Okay, so from a physical wiring point of view, all three of these features would look like a physical triangle, but logically look like a point-to-point connection. So in the case of the VSS, we would have our two 6509s that are connected together via the virtual switch link. Then these go downstream to whatever our end host is. Okay, so server 1. Then from server 1's point of view, it thinks that it has two ports that are physically connected to one switch upstream, and then we're configuring this as a port channel. So it's that physical triangle topology that we're changing into a logical point-to-point link. Now, the difference between the first two, when we look at either the VSS or the Stackwise config, is that both Stackwise and VSS use a single control plane and a single management plane. So what I mean by this is that when you connect the 6500s together with the VSL, or you connect 3750s together with the Stackwise cable, they're only going to have one management IP overall, and you configure the system as a whole. Okay, so you're going to see basically the fixed switches in the Stackwise as if they were modules of a modular switch. So your port numbering would be like gig 101, gig 201, gig 301 for line cards 1, 2, and 3. Okay, same thing is going to be true of the virtual switching system. You're going to see the line cards of chassis 1, chassis 2 basically look as two separate module numbers of the overall master switch, okay, the logical chassis. But the configuration is only going to happen from one interface. Okay, in the case of the virtual port channel, we have two separate control planes and two separate management planes. So this means that the control plane instances behind the scenes, like spanning tree, our IGB routing, BGP routing, first-hop redundancy protocols, we're running multiple copies of these. Now, if you were to compare this to the VSS or the Stackwise, if you had a router, okay, let's say that this is like your ASR 1K, and is physically connected multiple directions to your 6500s. Okay, so we have 6509.1, 6509.2. We have this configured as a channel. we have an IP address on the interface. Okay, so this guy's whatever, 10.0.0.1. These guys are 10.0.0.2. Then from a routing topology point of view, okay, so we have a channel there. From a routing topology point of view, when we run, let's say, OSPF, we only run one process global between the two 6500s, and they would be establishing only one layer 3 routing adjacency to the remote end. Whereas in the VPC, it would be two separate instances, okay, two copies of OSPF, two separate adjacencies, two copies of spanning tree, two separate path selections. So what this means is, from a configuration point of view, the VPC is a little bit more delicate in terms of the consistency that goes between the two switches, where with StackWise, since you're doing it from one interface, when you commit the config on one port, it's automatically advertising that change to all of the members of the stack. But with VPC, you need to make sure that manually the configurations are the same between the two of the peers. Otherwise, they're going to run into a consistency failure, and the end result is they would have to disable the active forwarding down to the end host. Okay, the end host is what we call attached on the VPC member ports. Okay, so from a config point of view, it means that they're going to have separate IP addresses on their management 0 ports. But the synchronization is going to be the same logic as how VSS does it over the virtual switch link. In the case of VPC, we call this the peer link. But behind the scenes, what this is used to synchronize is basically going to be the MAC address table. It's going to be the ARP cache. It's going to be the IGMP snooping cache, okay, for layer 2 multicast. Basically, we just need to make sure that the forwarding in the data plane is equal between the two of the peers, so that we don't have traffic land on one switch for MAC address A, we forward it this way, then it lands on the other switch for MAC address A and it goes the other direction. That's how we could potentially cause a loop in the layer 2 topology, or at a minimum start to drop traffic that we would cause a traffic black hole.